Good morning, good afternoon, good evening, good wherever you are, and welcome to another SNIA NSF, that's the Networking Storage Forum presentation. This one is part of our Storage Life on the Edge series, and it's about accelerated performance strategies. So if that title interests you and you think you're in the right place, well done. Otherwise, have a great day. This is a live webcast, July the 12th, 2022. Goodness, how time flies. So I'd like to introduce everybody. My name is Alex McDonald, and I'm an independent consultant and also a member of the SNIA NSF. Amanda is joining us from Edge AI Product Marketing at NVIDIA. She leads a product marketing group for Edge AI in Edge and Enterprise Computing Solutions, brings to life edge computing solutions that bring intelligence, great word that, I love the word intelligence, to hospitals, stores, warehouses, factories, and more. In addition to working on edge solutions, Amanda has held roles at NVIDIA, working with AI, data science, and virtual GPUs. Good morning. I think it's morning where you are, Amanda, isn't it?
It is. Thank you, Alex, and thank you for having me.
Yeah, good morning. We're also joined by Tushar Gohad, who is Principal Engineer and Storage Software Architecture at Intel. He's worked on networking storage most of his 20-plus year career. Doesn't look old enough, to be quite frank, about a 20-plus year career, but there you go. At Intel, he leads a storage software acceleration effort with focus on open source cloud, edge storage, content delivery network, software architecture, and performance modeling. He also provides leadership at industry working groups and various other things, like greening of streaming, which I quite like, because Tushar is going to be talking to us today about efficiencies in terms of performance per watt. So very much in green focus to Tushar's part of the presentation. Morning, Tushar.
Morning, Alex. Thank you.
And I know from Tushar talking earlier that he's in Phoenix in Arizona, where it is hot. So congratulations on being hot. SNIA. What is SNIA? SNIA, the Storage Networking Industry Association, is a group of 180 industry-leading organizations with about 2,500 contributing members overall and 50,000 IT end users and storage pros worldwide, of which you, the audience, are part. And you can learn more about what we do at SNIA at SNIA.org, and in particular the technical work that we do /technical. We've also got a Twitter handle at SNIA. What do the Networking Storage Forum do? Well, we're part of the SNIA. We're one of the forums within SNIA, and we cover things that are basically to do with the network side of storage. In other words, stuff to do with Ethernet, fiber channel, NVMe over fabrics, virtualized storage protocols, for instance, block, file, and object, and also data security. So it's a fairly wide-ranging brief, but the focus is on things that are networked. And today we're not going to disappoint you because we're going to be talking about things at the edge. And of course, to get to the edge, you need a network. As is usual with the SNIA presentation, this one comes with no warranties. And if you use parts of it, please read the legal text here. I'm not a lawyer, neither probably are you. So go and have a look at it. Make sure that you follow the rules that we outlined here. We'd be very grateful. Excuse me. So today, what we're going to be talking about, we're going to be talking about a continuum of acceleration strategies. And Amanda's going to help us understand what those are at the edge and about moving intelligence, well, the things that we do smart, to the edge rather than having it in the data center or some centralized compute and networking, compute facility or a data center. And we'll also be talking about accelerating edge content delivery networks, the kind of storage models that we require, the edge locations requirements and the constraints that brings, the edge storage choices that we have, how do we do caching acceleration, and also this thing about greening, how do we have software that gives us better performance per watt. So without further ado, I'm going to let Amanda take it away and talk about accelerating edge AI. Amanda.
Thanks so much, Alex. Yeah, I really wanted to start, first by saying, the focus today is all about edge, all about accelerators. And one of the unique things about the edge are the different requirements, the different workloads, and all of the things that run there. So there isn't a one-size-fits-all strategy when it comes to what type of acceleration you do for the edge. So today in our presentation, we are going to cover multiple types of acceleration options. So whether it's optimized software, integrated accelerators, discrete accelerators, All of these have their place in your strategy for what's going on at the edge. I'm going to spend a lot of my time on discrete accelerators because I'll be focused on AI. And then Tushar will cover a lot on optimized software and the integrated accelerators. So jumping right in, I wanted to talk about why we're seeing AI as such a huge topic at the edge. It's been almost an explosion in the last year or so of interest and excitement and people starting to move towards how do I deploy my AI applications at the edge. And so why is this such a huge topic? Why is this sort of eclipsing what we've seen so far in terms of data center or cloud deployments of AI? And the answer is really about the work that's been going on at the edge for the last number of years on data collection. Starting 10, 15 years ago, we saw organizations start implementing IoT devices, cameras, sensors in their edge environments. And these sensors are creating so much data that we no longer can actually process that data in an effective way in real time. Humans can look at that data, we can audit that data, we can look at it for historical information, but we're not proactively using it. And so we're not getting the total value that we see from such a massive data source like sensors at the edge. And so at the same time, we had AI coming up and then moving from research to training to actually deployment of AI. And what has happened was AI happens to love data sources. So when it came to looking at where to deploy AI applications, the edge became a natural fit. And what we started seeing was people looking at purpose-built AI use cases at the edge that provided this ultra low latency ability to have data ingested and respond with an inference or with an activation as quickly as possible in the lowest possible time. And that's where we started seeing a lot of sort of discrete AI hardware, chips that were being designed specifically for each specific use case. But the truth is, that was never the goal. We never wanted to just do one AI action at the edge. In fact, one of the things I like to say about AI is that AI is a little bit like a tattoo. You never have just one. What people are really trying to accomplish is these intelligent spaces, connected environments that have multiple sensors, multiple AIs, all running together in that environment, communicating with each other, and building these highly automated, highly efficient edge locations that we can actually use to improve the world we live in. And so as we move from each one of these phases of edge deployment, we're moving from sort of point AI and point hardware infrastructure requirements to looking at how do we build AI platforms at the edge, infrastructure at the edge that can run multiple applications, that can collect multiple sensors and provide that fully intelligent space. So I wanted to give a couple of examples of what intelligent spaces are because we hear about these all the time, but we may not realize that this is all AI and AI running at the edge. So whether you're talking about traffic flow management that's done in smart cities or for transportation, you're looking at, health management of livestock and plants in the agriculture space. Surgical robots certainly are something we're seeing starting to come up in hospitals. Patient health monitoring with the last crisis we've just gone through. AI has been really helping doctors and nurses, making sure that they're spending their time with the right patients. Smart stores are starting to come up, automated checkout, frictionless shopping. The Amazon Go store is a great example of a truly intelligent space where humans and AI are actually integrating together. And then, of course, the smart factory, I think, is another great example because you can imagine AI intersecting every space along from materials coming into a factory, having to be delivered to the right location at the right time so you don't have a gap in what materials are available or too many, into inspection of the application or of the products themselves, making sure that they're not getting defects, making sure that we're producing the right things, to predictive maintenance, ensuring we detect outages or downtime before we have to actually shut everything down. And that then continues all the way out to the supply chain side of the smart factory as you're putting those products out into market. So as you can see from each of these categories, this isn't about deploying a single application, a single robot. It's really about building a smart space. And that's why in these environments, we're seeing people look at data center infrastructure platforms deployed at the edge, sometimes in ruggedized fashion, but really providing that full compute power that's going to power the smart space, whether that's a city, a factory, or a hospital. These can be anywhere from single nodes to half racks to full racks to sometimes even a mini data center. But all of these are considered the edge environment. So now let's talk about the discrete accelerators that we see for the edge. And these are going to be common. Again, I'm not talking about the specific accelerators that are designed for and sort of purpose-built for specific use cases. This is the GPU, the CPU, and then what can be known as the XPU, the DPU, the SmartNIC, which I'll talk about a little bit more. So typically with AI, you're going to hear a lot about GPUs. These are high-performance applications that need the performance required, not the same performance required for training an AI application, but they still need that high level of performance so that they're responding to, as quickly as possible after that data is coming in. When it comes to sizing for GPUs, there's a couple of considerations that you're going to want to take into consideration, which would be, the size of the environment that you're deploying into, any power constraints, the temperature requirements that you're working with. GPU memory will typically be determined based on the number of sensors that are coming into that environment. So as an example, when you're talking about computer vision applications, typically you need at least half a gigabyte of GPU memory per stream, per camera stream that GPU is going to be processing. I mentioned the latency. How many inferences per second are you expecting in this environment? That will also be a sizing factor. And then again, in the area of video, you're going to have encoders and decoders, and those may be a factor in your choice. So once you've determined, okay, what are my GPU requirements? Do I need one? What's required there? We then get to the CPU. And at the edge, the CPU, we're specifically seeing this for the memory and system function. Typically, we'll see single socket, maybe dual socket for edge use cases, but these are often low power CPUs. And typically, we recommend anywhere from six physical CPUs cores per GPU. So when you're looking at that CPU, you do have to consider all of the applications that are running on it, and then ensuring that it's balanced with the other hardware that's running in that system. So then we get to the DPU or the XPU. And this is actually a great topic because it's something that SNIA is working on right now, is defining this category, because there are multiple names: SmartNIC, DPU, IPU, APU. But these are dedicated accelerator chips that assist or offload that CPU. So more and more, we're starting to see these come up at the edge because there may be CPU bottlenecks with heavy data sources like video, or we have areas where you need that zero trust security. And I am going to talk a lot about security in a little bit, but DPUs are a great way of ensuring that once the data comes into the system, it's fully encrypted. And even if somebody gets physical access to that system itself, they cannot get access to that data. So those are the environments that we see these. Typically, I'd expect a lot of smart city application, government applications, and then even the telco space with 5G at the edge. That's another great use for these XPUs. And by the way, there are some great resources on the SNIA website for XPUs if you want to learn more. So I want to talk a little bit about what are the general questions. And of course, there are many, many questions that come after this. But these are sort of general questions as you're thinking about environments at the edge, as you're thinking about how you size these AI platforms that are going to power these smart environments. And so I break down the questions into two categories. Once you've answered these, then you have to do all the details that come after it. But the application questions are going to be about what applications are you running today and what applications are you going to run in the future. Keep in mind, these are traditional x86 data center type systems or servers. They may be workstations, they may be microservers, but we expect those to run often 3 to 5 years in any given environment. So what applications are you running today? And then what applications do you envision you might be running in the future? Sizing to be able to at least scale to those environments is going to be helpful. How many streams of data will they process? And I'll see this when I give an example. But streams of data is a pretty basic calculation. How many sensors, data sources do you have coming in? Again, cameras are super easy to detect. And then how many applications need to access those streams? So for each type, take the number of streams times the number of applications, and that's how many streams of data need to be processed in that environment. Latency is a great question because that's what edge environments are all about. Ultra low latency can mean totally different things depending on your use case. In terms of autonomous machines, cars, you're going to be talking sub-millisecond use cases. But for example, in factories, I was working with a customer who was doing, their production line had to do an inspection every 21 seconds. That meant all they needed to do was get that high accuracy inspection in 20 seconds or so. By being able to do it in 10, 5, it didn't actually speed up the process at all because that time was dictated by the rest of the assembly line. So understanding that latency requirement, that latency window, is going to let you know what levers you need to pull with additional performance or power versus where you can, sort of dial it back. And then, of course, software optimizations are important. As you build out this infrastructure, there are going to be resources that are maybe overutilized or underutilized. So making sure that software is designed correctly and optimized correctly for those environments will let you get the highest possible performance within whatever hardware you build. Now, the other area to totally consider on the edge, and Tushar is going to go into this in even greater detail, is the edge environment itself. Are there power, space, temperature, thermal requirements that you need to take into consideration as you're building these platforms? Can you build one big platform that you run multiple things on, or do you have to build smaller ones that can be distributed around the environment? Do you have the same requirements across all locations? Many times this is not the case. Some locations may be bigger, some locations may be smaller. Being able to build a flexible platform that can scale up to your largest needs, but also support the smallest environments that you have is critical. And then, of course, what's the network connectivity of that environment? Connected environments, these are the easiest. You generally always have a network connection, so you can send data back and forth. But semi-connected and disconnected environments, you may have to consider the storage requirements of those edge systems, because they'll need to make sure not only are they keeping that data on site until they're able to send it off to any sort of central repository for future analytics, but you also need to make sure that all the applications that you're running at the edge can continue to run, whether they have that connection back to the cloud or data center. So I did put together a couple of examples, and this is just, again, these are guidelines to help you as you're thinking through what types of systems you might be looking at and what type of accelerator power you need inside them. So small, medium, and large, we start with the small. This has 6 to 7 video streams and only one application running on it. You can probably run this on a low power GPU, and therefore you need about 6 CPU cores to power this device. You'd expect it to be about a 1U form factor. Memory is relatively low, and then storage, again, looking at the lowest possible to make the smallest, most compact system that you can find. As you get up to the medium configuration, we're talking about 10 to 12 video streams with multiple applications. So because we have 2 applications, you're looking at anywhere from 10 to 24 video streams. which means we're going to look at 2U systems, probably running multiple GPUs in these systems. Typically, you can run multiple applications on a single GPU, but for these low-power GPUs, you're probably going to want to dedicate those for each one of the use cases. Here, you need to increase the number of CPU cores for these, increase the memory, and of course, increase the storage because you're expecting more data to be processed. Large follows a very similar pattern. Here, we've got 20 video streams running 3 applications. So this is actually 60 streams of data that need to be processed on the system. Here, you could run a medium or even a high-powered GPU and divide that GPU up among the multiple applications. You're still expecting this to be at least a 2U system, 24 CPU cores, more memory, more storage. So this is, when we're looking at how we size these environments, it's really a situation of what is the data, what is the AI, and what is the processing power required to support that. So as I've talked about the discrete accelerators, how we consider sizing, how we look at this, we have to see that, this is all a factor of AI reshaping what we think of as a data center, what we think of as a data center where it's deployed. We know AI requires massive amounts of data, and the good news is Edge has that. We have the sensors in place. We're already collecting that data. We're now just putting it to use. We also know that these data are going to be distributed. When we think of a cloud or a data center, you're talking about thousands of nodes in one location. The edge, you're talking about one node in thousands of locations, right? Or 1 or 2, which changes the way we think about management and orchestration of these environments and how we control them as an IT organization. Performance is paramount. AI intelligence can only work when we have the performance to actually have it respond with the inference in time for it to cause some sort of action. So if you don't fall within the latency window that I talked about for your application, it's no longer intelligent. And I think all we have to do is talk to any one of our various chatbots that we have in our lives to understand that time lag, it does make a difference. And when you're talking about AI at the edge, in certain situations, that difference can be safety and is just absolutely critical. The final thing that's important to think about when we're talking about the edge, and I know this is about accelerators, but this is critical, is AI is one of the most valuable applications that we're putting out there. And so we need to think about how we're securing these environments and how the security model gets turned on its head versus what we do in the data center. So if you think about a data center as the castle and moat model that we're all familiar with, everything on the inside is secure, everything on the outside is not. Edge environments break that apart. In an edge environment, you have to assume that anywhere, everyone can have access. This means that you have to look at what is the least possible trust, and zero trust is what we aim for, but we know least trust is probably what we're going to accomplish, so that we're verifying users as they're coming in, we're validating devices to ensure that not only are the right devices connected to whatever our management tools are, but also that those devices haven't been tampered with or changed since we last connected to them. And we have to limit privileged access. In a data center, you can often limit that privileged access physically, but at the edge, you're probably going to be working with partners, you're probably going to be working with third-party application vendors, and so we need to be able to provide access, but in a secure way so that it's done safely. Signed and measured software is another great thing. Checking to make sure that the software that we meant to deploy is the same one that arrived at that edge location, and that nothing was changed in the meantime. Encrypting data, no matter where it is. So whether it's in transit from being deployed down to that edge site or at that edge site, so that people who have physical access to the machine can't get access to those AI models, to that IP that our organization has. And then one of the latest areas of security that we're talking about a lot is about protecting the AI models in use. Often AI models are used by one company and developed by another. So we want to be able to get the inference from the AI model without seeing the underlying code and IP that's contained in that AI model itself. So being able to protect the model and still have it run and function is another critical piece of security. And again, SNIA has a lot of additional content that talks about security. And we could go on about this topic for hours, so I'll stop there. But I did. So just to summarize, AI is a big workload. It's transforming how we think about the edge. It's making us think about the problem holistically in how our edge environments are interacting together with multiple sensors, multiple applications. And it's important to think about what are the requirements to build the right systems with the right performance. So I'm now going to turn it back over to you, Alex.
Thank you, Amanda. That was very good. In fact, I've got a question for you. The how big, how fast question, the one of capacity and performance, is one that's plagued the IT industry for decades. We seem to still be doing chicken entrail stuff where we estimate how much we need and what we need just by literally sacrificing a chicken and then inspecting it. Are there good modeling tools in this area, or are people still doing this by rule of thumb?
So there are different ways of doing it. I think one of the best modeling tools can actually be the cloud. The cloud can be our friend in these environments. We can use, because a lot of what we're deploying at the edge is data center technology. We can test it in cloud or data center type environments to see what that runtime looks like. It does mean that you have to design the applications that you're running at the edge to be able to run in different scenarios. But I think that's one of the best ways. Otherwise, for most of our customers, the answer is build larger than you need for the POC and test. But almost every person I speak to does not realize how quickly the number of AI applications accelerates. So you're almost always adding more.
Okay, so it's a mixture of experience, some metrics from what you might call pseudo simulation, running it in the cloud, and the inevitable chicken entrails again.
Yeah, and then full simulation, but that's a much trickier topic, I think. Yeah. So digital twin will eventually come, but we're still in the early days there.
Thank you. That's really good plug. Actually, we're going to do sometime this year a digital twin presentation. So hey, good. Anyway, on to Tushar, who's going to take us through accelerating storage and caching at the edge, and in particular, talking about performance per watt, which I think is a subject that would interest most people because of the increasing requirement for power and also the increasing cost of providing that power in the first place. So Tushar, over to you.
Thanks, Alex. So Amanda did a fantastic job covering the machine learning inference use case at the edge, and so have a few other speakers and panelists in this series on edge, storage life at the edge. So I would highly recommend you, watching or listening to the previous talks in this series. They do cover both AI as well as computational storage in a fair bit of detail. One area at the edge in terms of the use cases as well as the deployment models that hasn't been touched yet that I wanted to cover was essentially edge cloud or edge storage for edge compute or general purpose compute at the edge, as well as the most widely deployed use case at the edge, which has been caching, right? So edge storage comes in all forms. If you look at the offerings from Cloudflare or Fastly or Akamai, right? They have object as well as key value sort of offerings for persistent storage for your stateless services, as well as what we call edge cloud. And there are also disaggregated as well as computational storage paradigms emerging, depending on the size of an edge site, or as workloads move closer to the data. Those deployment models are also kind of becoming more popular at the edge. Edge caching, which does remain one of the top edge use cases. I mean, think of Netflix having built their first CDN 10 years ago, or Akamai having built, has made sort of the web what it is today 20 some years ago. CDNs have existed at the edge as one of the foundational use cases, and so caching at the edge is sort of it's a use case in both directions, upstream as well as downstream. CDNs have done it for downstream delivery, a lot of times web pages or other interactive content or video, making it available strategically closer to the user to reduce the latency of delivery. Or in upstream fashion, where you may have storage gateways that cache content that is being ingested from IoT devices, or security cameras, or autonomous vehicles, and the likes, right? So where the goal is not to store petabytes of data at the edge. It's to store data sort of as it's making its way to the cloud, and it's typically stored for just enough duration to be analyzed in for let's say forensic reasons, or defect detection or prediction reasons. Typically, if you look at video ingest sort of use cases, you'll see storage at the edge being about 72 hours, and then all of that data basically being that storage being retired to for the next set of data, and any sort of compute after that happens in the cloud. So edge caching, both upstream and downstream, as well as general purpose edge storage, will be the focus of my section here. Now let's quickly review what Amanda covered in the beginning of the talk, because the subject of the talk is acceleration strategies at the edge as they apply to applications and the storage that they consume. There's a continuum here, from your most performant, most efficient discrete accelerator-based implementations like XPU, GPU, to more flexible and programmable software. Right. So the choice of these accelerators it really depends on your goals, right? Which I'll cover in more detail with some typical edge metrics that you consider. But overall, just to give an example, if programmability is important, then CPU might work for you better, because optimized software that's basically a software-only implementation is many times portable from CPUs to, let's say, bigger CPUs to power efficient CPUs to sometimes even power efficient cores on XPUs. You could potentially run the same software stack across the board, which may reduce the engineering costs by a mile. But then if programmability and those latency is important, you could potentially develop a combination of these strategies. So that's why the wording not mutually exclusive on this slide. So as an example, if you wanted to develop an AI strategy, you could develop a custom one API kernel for custom operations that are accelerated on GPUs, paired with optimized software that runs on CPUs. Now let's take a look at edge, right? Edge, as Amanda already covered in fair bit detail, is not uniform, right? As you move from the centralized data centers to the access, which is a lot of times in the telco world is known as MEC, right? Multi-access edge computing, to the device edge, right? Which is sort of this developing idea of the edge, right? The constraints as well as the latency requirements change drastically. So as you move from right to the left, you move into the realm of latency critical apps, you move into faster storage, such as NVMe drives, or more in-memory implementations, high performance storage, and more customized hardware and software. So again, kind of to recap, right, edge deployment needs are sort of unique. So if you look at the physical attributes that I have listed here, as you move from central data center to the access, there are more requirements put on the general purpose server infrastructure, such as there will be power and thermal constraints, there will be some regulatory considerations, as well as ruggedization requirements. And as you go towards the device edge, from the on-prem edge, if you will, there you will see custom form factors, limitations in terms of floor space, power, cooling, etc. So to summarize, basically the requirements and the constraints of the edge. There are requirements at the edge from a workload heterogeneity, which means you need to run a mix of workloads. Edge compute is that whole idea of being able to have a edge infrastructure as a service sort of deployment with a mix of workloads. Security and privacy as the angle Amanda already covered. Sustainability, which is a big push, doing more with less, doing more within limited power environment, or reducing the power requirement for a particular target application. And then being able to bring elasticity to the edge, which means scaling capacity up or down at the edge depending on the demand. So for instance, as a CDN provider, let's say that the like of an Akamai might want to have an edge instance, right, that can be enlarged or shrunk depending on the demand at the time. So typically that's measured in bandwidth, or there are actually similar elasticity examples that can be given for latency requirements as well. But all of these requirements have to be met within constraints I talked about, and again, the one big one that always is at the top of the priority list is the total cost of ownership. So when you look at optimizing your edge application and choosing an approach to acceleration for a function within your application or storage, you're working along the 4 optimization targets I've listed here typically, which are performance per watt, performance per dollar, performance per rack unit, which is essentially taking into account the floor space or the rack space you have available at a particular location. So if you think about a mobile tower, right, which is part of the mobile edge or access edge, you typically don't have enough space for even a person to enter that room. So you're probably going to have only room enough for a few custom form factor devices. So those are going to be like RU or rack unit challenge, if you will. So how do I get the best performance per watt and best performance per rack unit in that environment, versus an on-prem edge which is typically your central offices are points of presence across the world where CDNs are located. So those have a little bit more flexibility, right, in terms of let's say you can deploy a 2U server at a CDN edge site. But as we go into the future, as 4K or more interactive content like AR, VR, or cloud gaming basically puts more demand on these CDN networks, these requirements are going to become stricter. There's going to be the requirement to bring process more users or more streams on the server, more users more streams per rack unit. So as a bottom line, these edge environment constraints as well as optimization targets are going to drive the choice you make for an acceleration strategy. So some examples going into the details of each strategy and a combinational strategy, if you will. So if you consider a MEC edge cloud, right, where your floor space and cooling are a premium, right? Every watt is sacred. Every watt and cubic inch has to be doing something, right? So in those environments, you're going to find power efficient CPUs or XPUs with power efficient cores being used. So so your software needs to be highly optimized and CPU efficient, so that you make use of every CPU cycle available. So an example that I wanted to cite in the storage context is, say, the choice of programming model for I/O, right? So a lot of you would be familiar with SPDK and I/O Uring, as which have emerged over the last decade as popular programming models for high performance, low latency storage applications, which rely on user space pooling, lockless and asynchronous I/O approaches, and they make the best use of CPU and hardware, platform features. To give you an example, integrated accelerators on CPUs, such as DMA engines. So as an example, some of the CPUs have DMA engines that can do inline CRC or XOR calculations, which can RAID, which can like RAID, which can basically help accelerate a lot of the data path computations, and then clever memory allocation schemes so that you don't sleep, you avoid context switches, syscalls, and then zero copy strategies for networking, right? All of these innovations in software, right, towards a better programming model, have yielded significant benefits. And this is a strong consideration for the edge, because performance per watt is the key metric, and if watt is the constant, the denominator is the constant, one way to improve performance per watt is to improve the numerator, which is performance, which is the need for cores to achieve a certain level of IOPS, as an example. So in this particular case, I've cited a study we did, which is published on spdk.io, for the NVMe TCP target as an example, where application of I/O Uring yielded 65% better performance per watt, versus your traditional libaio based applications, and even better performance per watt, more than 81% better performance per watt with SPDK implementation. So certainly software investment in better software architecture does pay dividends. Here's another example where, if you look at the data lifecycle at the edge, this is a diagram that shows how an open source implementation based on MinIO can be used during an entire data lifecycle for ingest and analytics, which can be used for, let's say, forensics or research. The clever software innovation here is basically the switch to an S3 select based architecture, which a lot of you may be familiar and may have seen in some of the SNIA talks based on computational storage, where you offload filtering and some of the other operations like parsing, bitmap handling, or string compares, which are subset of those, to the storage itself, which means instead of bringing data to where your compute is, you take compute closer to the data, and so that's the first step in the optimization is optimizing software, which is a better software architecture. With a simple change, you can get a about 10x performance improvement, as MinIO has reported. And vectorization by using some of the integrated accelerators like SIMD implementations like AVX512 for parsing, bitmap handling, or erasure coding, which is a data integrity or data durability strategy that is used by many object storage systems. You can get pretty handsome speed improvements by simply changing how the software architecture works. So these are a couple of examples of how investing in software can yield a better performance per watt. Next, let's take a look at the two deployment models that I talked about: edge storage and edge caching, and how each of these acceleration strategies could be used within those implementations. So this is an example for NVMe or Fabrics initiator implementation at the edge. So think of each of your edge nodes being stateless with an NVMe or Fabrics running on the edge node, on the edge compute side, and you have storage which is disaggregated over NVMe or TCP to a storage array. Now, there is a lot of detail on this topic that some of my colleagues covered as part of an SNIA talk that happened in June 29th. I would highly encourage you to listen to that, which goes into details on each of these strategies. But at a high level, what I'm trying to show here is sort of the spectrum of these acceleration strategies: optimized software, integrated accelerators to XPUs, how those can be applied, and where they fit on the programmability to performance spectrum. So in the first case, you have optimized software, which is, say, SPDK to start with, as I talked about earlier, which runs on the host CPU. And crypto and CRC is also done on the host CPU with traditional OpenSSL, user space sort of implementations. Whereas if one strategy to optimize it further could be to use AVX512 based vectorization and instruction set level optimizations such as AES or SHA instructions that are offered on the modern CPUs to speed it further. But then if your edge constraints allow you, your, let's say, rack unit, your form factors allow you to actually have a discrete XPU on the PCIe bus. Again, granted, you have PCIe lane availability, and you're short on the number of CPU cores, would be great reasons to look at the third model, where an XPU could basically integrate not just efficient CPU cores and offloads, but it might also be able to offload an entire network path as well. So as you can see, in the third case, an application running in a VM or a container or bare metal at the edge simply needs to have be able to talk have a kernel, right, that can talk NVMe protocol, and an XPU can offload basically the NVMe or TCP stack, all the crypto as well as CRC functions, as well as run the TCP and the network drivers on the XPU cores. Another example, which a lot of you may have seen from the talks from the likes of Netflix, is video delivery at the edge. This is where most of the storage footprint is today at the edge, which is video and caching. So what this slide is focusing on is the video on demand workload, where HTTP as HTTP2, HTTP3, upcoming as the protocol that is used for delivering content over the internet the user. So from origin to the user edge, there are multiple tiers of CDNs. A lot of times there is a mid-tier edge, and there's an edge, right, far edge, where these nodes are located. They usually have local storage in them, a general purpose CPU, and sometimes XPUs, depending on the edge location. And these nodes, they do run software such as Nginx or Apache Traffic Server or Varnish, right? So those are the higher level stacks that make use of storage tiering many times. So these are full featured storage stacks. Now, local storage is the paradigm in the space today. Disaggregated storage is making its way. So a lot of what I talked about on the previous slide also applies to this model. But I wanted to cite video delivery as a real example of how each of these acceleration strategies, what sort of performance per watt improvements they can yield. So a lot of this work was done with Varnish and Nginx. Some of this is done by Intel. Some of these measurements are also were based on some of the measurements reported by Netflix in the public talks. So in the first picture, if you look at optimized software, a lot of these stacks, such as Nginx or Varnish, to begin with, there were several bottlenecks. So if you look at the bottleneck that I'm trying to point out with those arrows that I'm showing, this is a very memory bandwidth bound workload. There is a storage to memory to storage to memory, memory to memory, and memory to network transfers for storage access, TLS processing, as well as transmit processing, which basically make this workload very memory bandwidth bound, CPU bound, as well as it's very sensitive to NUMA locality of the workload from both CPU, memory, as well as IO perspective. So we did a lot of work in this space to make these CDN stacks network aware, as well as we optimize the TLS pipelines to take advantage of the built-in accelerations such as AES-NI or QAT. So as the bottom line for each of these strategies shows, we saw about 35% headroom for performance or baseline stacks upstream just by optimizing software, which is a big number. And then integrated accelerators such as there are accelerators such as vectorized AES, which is a new set of instructions introduced by modern CPUs, which help you use a strategy to combine AVX512 sort of instruction sets with crypto instruction sets to optimize the performance like even further, around 15% or so. And the best implementation, of course, is to offload that crypto as part of a zero copy transmit method to the XPU, where the memory bandwidth demand as well as the core, so basically the CPU core demand actually goes up significantly. So this is a real example of how software re-architecture can improve your performance per watt by a mile, and it can have an impact on performance per watt, performance per dollar, because you're essentially saving on CPU cores, as well as a lot of the infrastructure. You can do a lot more with less, such as, for instance, the box that can deliver, let's say, a 100 gig can actually now deliver 50% or more with the same core count, which basically means it can deliver high-res content or more. It can serve more users from more streams. So to sum this up, there is a focus on sustainability and performance per watt, which remains one of the top design considerations at the edge. And there's a choice to be made here, right? Which is performance per watt is not necessarily free. Maximum performance per watt might mean giving a performance to meet a power budget, or compromising on cost, right? So it's all about balance. You should not underestimate the impact of the time and effort that you spend on software optimization to put every cycle of the CPU or XPUs to use. So with that, I'll hand it over to Alex to summarize it.
Thank you very much, Tushar. What I'm fascinated by this slide, by the way, is that it shows that we have moved from the point where hardware defined the software that we run. The software gave us the algorithms. The algorithms are now actually driving the hardware again. It's quite a fascinating circle we've been through over the last few decades. But thank you very much. So what I'm going to do now is just very quickly summarize this. I think we've seen from Amanda and Tushar's presentation that there is a real demand for acceleration at the edge, that the edge has not just become a point of data collection and everything moves to the center, but we're actually processing stuff there. And that puts a new set of constraints on us that we didn't really have in the data center. And the one that Tushar's particularly pointed out is power. You know, how do you get enough performance per watt to justify the number of watts you need to put out at the edge? You know, we don't have data center type budgets for these kind of power criteria that we might have. So moving to the edge, moving intelligence to the edge, and then having this strategy of trying to make sure we perform as efficiently as possible is really key to all this. And I'd like to thank both Amanda and Tushar for taking us through this presentation. It's been excellent information. Talking about excellent information, and Tushar mentioned this a couple of times as well, there are previous presentations. Amanda talked about security. There's one on security challenges. And we've got managing data from the edge to the cloud and back, because sometimes you need to get the stuff going in both directions. And we've also got some edge use cases presentation that we did. So please enjoy those. The slides, by the way, are available on one of the tabs. You should be able to see them as an attachment and use them to get these links so you can go and see exactly what it is we've been talking about storage at the edge in previous presentations. So please rate this webcast as you leave. Please tell us what you think of it. On a scale of 1 to 5, 1, I wish I'd been doing something else. 5, excellent. More of this, please. I've thoroughly enjoyed it. And thank you very much indeed for being with us today. Thank you, Amanda. Thank you, Tushar. And thanks to our audience. Good night.